Here is a pulley. At t is equal to time, I wanted to find the free body diagram. This is M1, this is M2. Can you find the equation for tension force?
Basic intuition. We know that if one mass is heavier than the other, that side will go down, while the other side will go up. But additionally, we know that if one side moves down at some acceleration, the other one has to move up with the same quantity of acceleration, magnitude of acceleration. Because otherwise, the distance between them would change, and that would mean that the length of the rope would change in the middle of the pulley's flight, which doesn't make sense at all. The pulley's rope can't stretch like a rubber band. It's already taut or pulled to its max length at the beginning. So that means that the acceleration of one has to be equal to the negative acceleration of the second. So what's the acceleration of the first one? Well, let's draw its free body diagram. We know there's gravity acting downwards and the force of the rope, tension, acting
Let's call
upwards.
it Ft.
Then you have M2, which is very similar. You have gravity pulling down this way and Ft pulling up this way. So you might ask, what's the difference between these two? Well, for M2, the force of gravity is bigger than the force of tension, while for M1, it happens to be smaller. And of course, you may ask the natural question, what happens when M1 is equal to M2? Wouldn't they have the same force? And indeed, that will align exactly with your intuition that if you put two of these, or two bodies of the same mass on this pulley, they will eventually just even out. Neither side will be weighed down. So
now can you use the F equal ma?
Yes, that's what I was about to do.
Okay.
So, now, if we multiply both sides by m, well, we can't do that actually, that's the problem. Here's what we're going to do. We know that the net force on M1 is Ft minus M1z. So that means that M1A1 is equal to Ft minus M1z. In other words, A1 is equal to Ft over M1 minus g. Now here's the thing. We can do the same thing with the net force on F2. But the difference is, since M1g is less than Ft in this scenario, this is positive, while here M2g is greater than Ft, so this is negative. So you get that A2 is just Ft over M2 minus g. And now the picture comes together because all you have to do is set A1 equal to negative A2. Since they're traveling in opposite directions, naturally the sign of their acceleration has to be different since they're traveling in opposite directions. Oh, I repeated myself. So you get Ft times 1 over M1 plus 1 over M2 once you bring this term to the other side. And then you bring this term to the other side and get 2g. So then, just use your knowledge of common denominators to state that this is, of course, M2 over M1, M2 plus M1 over M1, M2. And so, f of t is equal to, multiply both sides by the reciprocal of this, and you get 2g times M1, M2 over M1 plus M2. So in this case, what is it? Approximating the acceleration due to gravity is 10 meters per second squared. We already know what this fraction is. You get 2 times 10 times, and make sure you're always using the same standard of units, by the way. You can't use meters and then kilometers in the same equation, or you can't use meters and then inches, or you can't use kilograms and then use grams or pounds. That's how things go. Because then the derived unit that you have once you calculate the whole thing doesn't mean anything. Like, you can't multiply meters by int and claim it meter squared. So you get 2 times g, which is 10 times 6 times 4, or 4 times 6, whichever way you like it, over 6 plus 4. And of course we can take the nice shortcut and say, since 6 plus 4 is equal to 10, we can cancel those out, even though that doesn't have any meaning in real life. It's just that the sum of these two masses happen to be equal to our approximation for gravity. So you get this, which is just 48 newtons. And, of course, since it's the same rope connecting both objects, Ft is the same for both objects. But as you know, M1g and M2g are not, because the force due to gravity is dependent on the mass. So this is what? 4 times 10, which is 40 newtons. And this is what? Well, it's 6 times 10 is 60 newtons. So, what's the acceleration? Well, since the acceleration is the same for both sides, you can calculate A1 or A2 and it won't make a difference. Personally, I'm going to calculate A1. What's that going to be equal to? Ft, which we know is 48 newtons, over M1, which we know is 4 kilograms, minus g, which is 10 meters per second squared. And of course, a newton is a kilogram multiplied by a meters per second squared, which means that you can ensure that the units here are right, and thus A1 is just 12 meters per second squared minus 10 meters per second squared, or 2 meters per second squared, which means that M1 accelerates upwards at 2 meters per second squared, while M2 accelerates downwards at the same rate.
Alright, nice. So we have many more problems to do, so I'm gonna create some space. At least 50 problems to solve.
50?
Yeah. So Suborno, give me space. Suborno found the acceleration. You also can find the acceleration is equal to g big M minus small m, m1 plus m2. And Suborno said g is 10, so let's use 10. 6 minus 4 is 2. 6 plus 4 is 10. So acceleration is 2. Okay, the next thing, Suborno, you're going to find this is 1. Next thing you're going to find, okay, before we do that, let's cut that in half. Over here, as you mentioned that Ft is bigger than Fg, so that Wt has to be bigger than Wg, so that if you are...
Oh, you mean...
W, work done by tension is greater than work done by gravity. That means if I put you in this box, you're going to experience... you're gonna feel heavier.
Heavier, and of course, a way to work that out is imagine you're in an elevator and that elevator is going up over time. So like draw a diagram of you in the elevator cabin. So this is you, and you jump up, but then you realize that the cabin is also moving with you, which means that your jump height respective to the cabin is much lower than your jump height with respect to the elevator, with respect to the elevator rope. So in other words, somebody watching you from the ground would see that your jump was normal height for a human, but somebody watching you from the elevator would see that your jump was much smaller. And of course, if your jump is smaller, you're heavier. Now, of course, this is not rigorous at all, but it's a good way to remember things. And the same way, if your elevator is going downwards, and you jump, think about what will happen. If your elevator is going downward, well, I can't make it that dramatic. If your elevator is going downward, suddenly your jump height with respect to the cabin is much more impressive than your jump height with respect to a rest observer. So somebody watching you from the floor would observe that you jumped much less than somebody observing you from a camera inside the elevator. And so if you jumped less, you probably have less weight, apparently. So that is a good way of remembering.
Okay. So can you find the velocity of the mass 1, velocity final of mass 1
Well, here's the thing.
at the end of 2 meters?
Mass 1 and mass 2 both start at rest.
Right.
And they accelerate with the same magnitude in polar opposite directions. Which means that m1's final velocity is equal to negative m2's final velocity. But that's not what matters. Of course, you can find the final velocity given the acceleration and the distance by just using this equation. Or, of course, if you wanted something a little bit closer to the roots.
No, that's fine. Vf squared is equal to Va squared plus 280. That's fine.
Sure. So then you can just plug everything in. So we know that the initial speed is 0. We're trying to find the final speed, so we just take the square root of 2 times the acceleration, whose magnitude was 2, and we don't want to make anything negative because we have a square root here. If you really want to be nitpicky, I guess you can add an absolute value. And the displacement, or the distance, is 2 meters. So you've got the square root of 8, which is 2 times the square root of 2, or approximately 2.828.
Alright, so the velocity final is 2 root 2. That's what you found. Can you find the time when the velocity final is 2 root 2?
Well, that's also pretty simple. We know from the basic definition of acceleration that average acceleration, and of course average acceleration is equal to instantaneous acceleration in the case that it's constant, like in this scenario, the acceleration is always 2 meters per second squared, so there's no need for an average. Because, I mean, if you have the numbers 2, 2, 2, and 2, can you tell me their average?
2.
Exactly. So average and instantaneous mean the same thing whenever our quantity is totally constant. So we just have this. And so Ti is 0, at least we're setting it to be 0 in this case, which means I'll just write the time elapsed as t, and so we rearrange everything a little bit, and we get this equation. And of course, we actually know that the initial velocity of both objects is 0. So we can reduce it all the way down to this. And even more so, we already know that the acceleration of both objects has a magnitude of 2, and the final velocity of both objects has a magnitude of 2 root 2. Which means that the time has to be the square root of 2 seconds, which is approximately 1.414 seconds.
So now what we're going to do, we're going to divide and conquer. So this is m1, this is m2, and this is m1 plus m2. Here, as you inform the audience, fg is bigger than ft, and you inform the audience wg is bigger than wt. That means you inform the audience you would feel lighter if you happen to be in the box. Can you find problem number 4, work done by gravity on mass 1?
You have to keep in mind that the work done by gravity was in vain, because the object still ended up moving upwards anyways. So it's like gravity totally failed at its job.
So can you mention 3 hypotheses? If force act at the direction of the displacement,
It's not a hypothesis, it's a mathematical formula.
that's right. If
So here's the thing.
3, you can write them down, these 3
Please,
rules.
well, please give me one.
Sure.
Okay, so this comes from the definition of vectors and dot products mostly, but essentially the work done by a specific force F is equal to that force's vector dot producted with the displacement vector of our object. Like, for example, if we have a 2-dimensional system, we applied a force this way, and it turns out that our object moved all the way here, then the work is simply the dot product of these 2 vectors right over here. And it turns out that the dot product, which is a number, by the way, not a vector, you can also call it scalar, it turns out that this is actually equal to
Okay.
So by this rule, we can now figure out that if the angle between the force and the distance is equal to 0, you get that this is just equal to FD.
Or positive work done.
If they are perpendicular, which you may also hear as orthogonal, then their dot product is 0.
So that means 0 work done.
And if they're anti-parallel, then that gives a negative constant.
So that's negative work done. So 3 hypotheses. If force act at the direction of the displacement, positive work done. If the force act opposite at the direction of the displacement, negative work done. If the force act perpendicular at the direction of the displacement, 0 work being done.
I mean, if you really wanted to prove this, I mean...
No proven.
Okay, you could derive the definition of the dot product.
Oh, okay. So yeah, prove that FD cosine theta.
It's long.
Okay, that's fine. We can do it separate video. So work done by gravity.
Okay, well, the work done by gravity...
No, you can erase it. Okay, work done by gravity.
Well,
FGD cosine theta.
what's the work done by gravity in this scenario? And I'll actually give you a taste of how we'll do it later in physics. So, here's what we have. What's the force? Well, the force is directly downwards, right? And we're just going to consider this to be the y and this to be the x, like normal. So then that means this is pointing directly in the negative y direction. So to express it as a vector, you'd say it has 0 in the x direction and whatever the force is in the negative y direction. In this case for m1, it might be 40 newtons. So then, what's m1's displacement? Well, we'll figure out that m1 went from here before to 2 meters above where it was originally standing after. This is the displacement vector. Happens to be directly in the positive y direction, being 0, 2. So now, all you have to do is take the dot product of these two. The dot product of 2 vectors, A, B, and C, D, is actually really simple. It's just A times C plus B times D. So, what's the dot product of 0, negative 40, and 0, 2? Well, you multiply these, gives you 0. You multiply these, it gives you negative 80, which means that the work done is negative 80 joules. Simple as that.
And that agree with our hypothesis that the force did not act at the direction of the displacement, so negative work being done.
Well, yeah.
Okay, and that was our second hypothesis, and so I'm gonna go ahead and I'm gonna write this finding, and that was how much I forgot.
For
Negative 80.
for mass 1.
Number 5, can you find the FT?
Well, we found it very long ago. It was
48 Newton, good. That came from the equation Ft is equal to mg plus a.
No, we did this.
That's another equation, right? Okay. Number 6, find Fwt.
Well, the work done by tension. Let's see if we can once again get a taste of what you'll do in real physics. So, what's happening here? Well, Ft acts directly upwards, right? So, there's nothing in the x direction. It's all in the y direction.
And rope cannot push, so.
And the force is 48 newtons. So, we write the force vector like this. And, of course, the displacement vector, as we said before, is 0, 2, since it went up 2 meters from its original position. So, taking the dot product, the product of 0 and 0 is 0, and the product of 48 and 2 is 96, making this 96 joules.
Alright. So that's awesome. We now want to find the net work done on mass 1.
Well, just add the two together to get 96 minus 80 joules is 16 joules.
Now, I want to ask you a very simple question. I want to save the space. How much kinetic work was responsible for velocity 2√2 on mass 1?
Well, okay, the kinetic energy of mass 1 before or after?
How much kinetic energy was responsible for velocity 2√2
Sorry?
on mass 1?
Velocity is what gives kinetic energy.
Yes, that's right.
Does not create velocity.
That's right. So how much kinetic energy behind 2√2?
Well, half.
No. It's just 16 joules.
Yes, you can do that by the work energy theorem.
Okay.
But you can also just do the math yourself.
No, we want to show the work energy theorem as well.
Well, if you want to show the work energy theorem, you have to first show that the traditional kinetic energy is equal to the work energy.
So that's going to give you 16? All right. Number 9. Momentum initial.
The initial momentum is always 0.
Momentum final. Everything is on mass 1, so.
Well, it's just 2 times the square root of 2 times the mass, which is 4, which is 8 times the square root of 2 Newton seconds, which is about...
No, it's fine. It's fine. We don't want to use decimals. We don't need to. Number 10. Impulse on mass 1.
The impulse on mass 1, well, when what?
Impulse when at 2 seconds.
The impulse that was exerted on it by that force.
Yeah.
So, well, that's just the amount of force that was exerted on it, multiplied by the time that